Hi, my name is Ngozi and we are going to talk about microplastics and heavy metal removal from wastewater and freshwater using a membrane.
I'm Kizomoy. I'll do the methodology part of this presentation. I hope you like and subscribe and share.
Hi, I'm Lissejo Mabani and I'll be talking about the discussion.
Hi, my name is Raquel Hanan. I'll be also talking about results and discussions.
I'm Dumgai Senkambule and I'll be concluding on the removal of heavy metals and microplastics using a membrane. Presentation focuses on the introduction and purpose statement, the chemicals and reactions, methodology, results and discussion, and also the conclusion. We have also included our references and also acknowledgements. Please keep on watching.
Microplastics are non-biodegradable pollutants found in freshwater and wastewater. They pose a danger to sea species and also humans. Research has shown that when these species consume the microplastics, they end up having diseases such as reproductive damage and obstruction of organs. Microplastics contain toxic additives that are used in plastic production. They end up affecting humans through the food chain. Studies have detected that the human stool contained microplastics. This shows that humans are directly affected by the microplastics. Microplastics are divided into two categories, primary and secondary category. The primary microplastics are found in personal care products and the secondary microplastics form when the larger plastic waste is exposed to the sunlight, wind, and water. The growing concern is that even though the microplastics contain toxic additives, they also contain other toxic components. For example, bisphenol is added to hardened plastic water bottles and food plates. If bisphenol is ingested, it affects the brain and development of the fetus in humans. Another example is when additives such as calcium carbonate and lubricants such as sodium stearate are added to plastics to reduce cost. After consumption of microplastics by humans, the calcium carbonate and sodium stearate can leach out of the microplastic and negatively affect the human body by causing cancer and corrosion of the internal organs. Microplastics enter freshwater system through various sources. The main source for contamination of rivers are wastewater treatment plants effluent, sewer leaks during heavy rainfall, and sludge runoff. Approximately 80% of microplastics in the oceans are believed to originate from land-based sources, while the remaining 20% comes from activities related to agriculture and fishing industries. Standard methods for removing microplastics include techniques such as agglomeration into biological flux, oxidation combined with fluorescent staining, polycarbonate filters, and filtration using a 0.5 uni-millimeter filtered paper. However, these methods have disadvantages, including the production of secondary waste from chemical use and the instability of filtration materials. Membrane technology offers an alternative for separating microplastics from various water sources. Membrane separation is becoming a preferred technique for removing microplastics due to its scalability, low energy use, operational flexibility, and capacity to handle large water volumes. Studies have shown that membrane-based filtration can reject up to 99% of microplastics, making it the best effective method for use in the tertiary treatment stage of wastewater treatment plants.
I'm Mr. Moy and I'm going to be speaking about the chemicals and reagents of this experiment. In this experiment, we have PVDF membranes, carbon nanoions, sodium chloride, iron sulfate, heptahydrate, hydrochloric acid, hydrogen peroxide, ethanol, and deionized water and nitric acid. PVDF membranes. These membranes are used for filtering microplastics from water due to their superior strength, flexibility, and resistance to aggressive handling. The 0. 0.45 micromolar pore size ensures effective filtration of even small microplastics, and its hydrophobic nature enhances the filtration process. Carbon nanoions, these are added to the PVDF membrane to improve performance. They also form a positively charged layer that enhances the filtration. Iron sulfate heptahydrate, this chemical acts as a coagulant to precipitate microplastics from the water, facilitating their removal. Sodium chloride increases the density of the water, which helps microplastics to float and separate from the solution, making them easier to collect. Hydrochloric acid and nitric acid, these strong acids are used in the acid digestion process to extract and analyze heavy metals attached to microplastics, breaking down organic matter. Hydrogen peroxide, the oxidizing agent, is used to break down organic matter and turbidity in the water samples, helping to separate microplastics from other contaminants. Ethanol is used to clean and prepare the samples and membranes. Ethanol assists in dispersing the CNOs onto the PVDF membrane and ensuring that the filtration materials remain clean and functional. Deionized water is used in preparing all solutions, rinsing containers and cleaning, ensuring no contamination in the samples during the filtration process. In this experiment, for the sample collection, water samples were collected from 3 sources: influent and effluent at the Dashboard Wastewater Treatment Plant at Pretoria, Sterkfontein Lake, Johannesburg, and tap water from Doornfontein. Samples were collected in pre-rinsed 5-liter and 3-liter containers. And for the sample preparation, the wet peroxide oxidation method was used with 80 milliliters of 0.05 molar iron sulfate and 30% hydrogen peroxide added to 400 milliliters of sample water. The solution was heated to 75 degrees Celsius and 6 grams of sodium chloride was added for microplastics flotation. For the modification of PVDF membrane with CNOs, 10 milligrams of carbon nanoions were dispersed in deionized water and ethanol, sonicated for 20 minutes and filtered through the PVDF membrane to improve filtration efficiency. For the filtration of microplastics, samples were filtered through PVDF membranes and PVDF CNO membranes using a vacuum pump. Membranes were dried for 24 hours and made to assess the amount of microplastics collected. For the extraction of heavy metals from microplastics were digested using 12 molar hydrochloric acid and 16 molar nitric acid heated to 50 degrees Celsius. Samples were taken at intervals and analyzed using ICP-OES. For the characterization techniques, membrane performance, porosity, pore size, water permeability was measured, and microplastics were analyzed for shape, color, and composition using SEM and ATR-FTIR. Heavy metals were quantified using ICP-OES. The quality control, ICP-OES was calibrated with multi-element standards. Limits of detection and quantification were calculated to ensure accurate measurements. For membrane performance, porosity, pore radius, and water permeability were evaluated using specific equations, measuring flask at 40 kPa pressure. For microplastic characterization, microplastics were analyzed with a stereo microscopic and SEM. For morphology and polymer composition was confirmed with ATR-FTIR. For analytical figures of merit, LOD and LOQ were calculated using specific formulas based on blank sample concentrations and standard deviations.
For major sources of microplastics, we have synthetic fibers, tire dust, and city dust. We have synthetic dust at
35%. This is the largest contributor to microplastic pollution, which comes from synthetic fibers, primarily originate from washing synthetic textiles such as polyester or nylon during laundry. When clothes made of these materials are washed, microplastic fibers are released into water, entering aquatic environments. And second, we have tire dust at 28%. So this is the second largest source, which results from the abrasion of vehicles' tires on roads. This wear and tear produce tiny particles that are eventually washed off into water systems or dispersed into the atmosphere. And we have city dust at 24%. This is like our third largest. So this includes variety of small plastic particles from construction materials, plastics used in urban infrastructure, and other sources that are eroded or dispersed into city landscapes. So this one basically occurs mostly at urban environments or urban areas.
From the obtained results after the filtration of microplastics from wastewater influent, it was confirmed that the water samples had 16% cellulose based on the carbon-oxygen stretch and the carbon-hydrogen band. The cellulose that was found comes from the cotton which arises from laundry water that is disposed of in the water system. 50% of high-density polyethylene was discovered from the values of carbon-hydrogen stretch and carbon-dihydrogen band. High-density polyethylene is a microplastic that is very commonly used for packaging. Examples of this packaging may be your plastic bags from grocery shops, bottles, or containers. Another material that is commonly found from toothbrushes, hairbrushes, and artificial lashes is polybutylene terephthalate, which had a percentage of 16.6% in the water sample, which shared the same percentage as nylon 12. This graph is the ATR-FTIR spectra of microplastics obtained from a wastewater influent sample. This graph shows us how the percentages of nylon, high-density polyethylene, polybutylene terephthalate, and cellulose were determined using the values shown. For the heavy metal analysis, it was found that copper, arsenic, and magnesium were highly present in the wastewater sample. When compared with the acceptable limits of drinking water, you can clearly see the amount of contamination caused by these metals, and that can cause a lot of illnesses for humans when consumed, such as liver damage and neurological issues. Long-term exposure of arsenic can cause skin lesions and respiratory issues, or worse off, cancer. Magnesium is important for bone health and energy reproduction, but too much of it can cause diarrhea or excessive cramping in the stomach. Zinc is beneficial for the immune system since it easily fights off infections, but too much of it for a long period of time, however, lowers your immune system. Other effects include headaches, upset stomach, or loss of appetite.
In conclusion, the PVDF membrane successfully removed microplastics from wastewater and freshwater systems. This is due to its crystalline and amorphous, which is the shapelessness character of the molecule. The microplastics in the influent are composed of high-density molecules such as polyethylene, poly, nylon 12, and cellulose. High concentrations of heavy toxic metals such as arsenic, copper, and zinc, originating from the local mines, were attached to the microplastics, causing a significant concern. Incorporating a microplastic trap in the water before releasing it to the environment or municipality can improve the wastewater treatment infrastructure. This research can be used to apply protocol to ensure the compliance of water quality and management practices, decreasing pollution in the environment. Thank you.